Hi and welcome to another of BYJU'S live sessions. Today we are going to talk about electrostatics. Now electrostatics is a study of charges, right? I am not going to go into the detail of what a charge is and actually this chapter is not designed to go into the details of that. So what we are going to say here is that charge is just a property of a material like mass. You don't ask what mass is, right? Similarly, we are not going to ask what charge is. Rather, what we do in this chapter is that we study the properties of charges. Okay, what is the behavior of charge? And broadly, if I talk, this chapter has been divided into some sections, and I would like to lay that out in the beginning. So we begin this chapter by studying first the basics about charges, what are its properties. Then we go a little ahead and then we talk about the electric force, right? Then we talk about the electric field. Then we talk about electric flux. We talk about Gauss Law. Then we talk about electric potential. And then in the end we discuss a little bit about conductors, right? This is a fairly big chapter. It's one of the earliest chapters in 12th standard, usually the first chapter which is taught in 12th standard, and it's a big chapter, and you should take enough time to understand this chapter. Actually, the concepts are not very difficult, and I would say that this chapter is electrostatics is basically 35% of new concepts and the rest, which is 65% of mechanics. Okay, so if you are good in mechanics, then you're probably going to be good in electrostatics if you understand some few basic concepts. Okay. Another warning about this chapter is that, see, another general warning about all the chapters which we are going to learn in 12th standard, most of the chapters, is that the chapters in 12th standard are about things that you cannot directly see. You cannot directly observe. You cannot see a charge. You cannot see the interaction of charges. You cannot. You might not have ever directly. You have encountered, of course, but you might not have realized when you're encountering an electrical force, right? The very reason that when I hit my hand with my fist and it doesn't go through it, it is because the atoms are repelling each other, and that's an electrostatic repulsion, right? But you might not be very aware of this. You might not even find it very fascinating because it's an everyday things, right? It is the charge with which the really tiny subatomic particles, they interact, the protons and the electrons, right? But when you were in 11th standard, you see, you have studied about forces and forces like gravity. You've studied about Newton's laws, which you can see how with a car moving. You've studied about waves, which you can see on the string. You've studied about sound, which you hear and you can like make out and you can make sense of what you're learning. But when you come to 12th standard, things might look a little abstract. Things obviously make sense if you follow it from the basics, the basic axioms and all the logic. All the logic would make sense. But yeah, it will be difficult to see it around your daily life, except for like chapters like electric current and all, which in which you can make some observations, and even in magnetism you can make some observations, but it is not as obvious as things have been in 11th standard. Okay, having said that, let's start. So now, charge. Now there are some properties of charges. First thing we have to know is that there are two kinds of them, right? And only two kinds good for us. There's a positive charge and a negative charge. We have just named it positive and negative. It has nothing to do with mathematical positivity and positiveness or negativeness. It's not like anything like that. Okay. But there's a reason we call it a positive and negative. The reason is so when you have an atom, right? If an atom has 5 protons and if it has 5 electrons, then we say that the atom is neutral. Okay, it behaves as if it has no charge. When we go and we investigate one proton, we find that a proton has a charge, and the charge is equal to a number which is equal to 1.6 into 10 to the power of minus 19 coulombs. Okay, that's a strange number, but that's the charge of a proton. And an electron has the same charge, but negative version of that, which is minus 1.6 into 10 to the power of minus 19 coulombs, right? So when you have an atom with 5 protons and 5 electrons, right, you have equal positive charge and equal negative charge. So overall the atom is neutral. So in a sense you can say that if you have 5 plus 5 charge and minus 5 charge, when you add both of them you get net 0 charge, because it becomes neutral in a sense. So in that sense being positive and negative has that meaning. Now we know that a positive charge, they repel. A proton and proton will repel. An electron and a proton, they will attract. Okay. Again, with the sign, if someone says that a proton has the charge in a proton is greater than the charge in an electron, you can't say that proton having a positive charge doesn't mean that it has a greater charge, right? Because it's not mathematical plus or minus. So like charges, they repel. Unlike charges, they attract. Positive negative attracts, positive repel, negative repel, right? Simple. Now another thing is, say the thing is, let's say you have some charge, and let me clarify, because I'm not going to go into the detail of this. The unit for charge is a coulomb, okay, named after the physicist Coulomb. 1 coulomb is the unit of charge. Now if you have, let's say 5 coulomb of charges somewhere. Now 5 coulomb of charge could have any number of protons, right, or any number of electrons, right, but it cannot have a charge, it cannot be made up of half electrons. What I mean to say is that the charges always come in the multiple of the charge of a proton or a charge of an electron, which are basically equal, right? So you can have like, or charge of a proton or charge of an electron is represented by an E. So you can have a charge of 2E, you can have a charge of 3E, you can have a charge of 4E, 5E, 6E. So always a multiple of E. So if you have 5 coulomb, you will be sure that this is equal to some number times E. It can be 1000 E, it can be like 1 million E, something, but it will be some number times E. It is like you live in a country where the minimum denomination is 1 rupee, okay, and there's no other denomination, there's only 1 rupee. So if I say that you have 10 crore rupees, then I know that you have 10 crore coins of 1 rupee. When I say you have 10 rupee, you have 10 coins of 1 rupee. You cannot have 10.5 rupees because you cannot have a half coin. Similarly here, you cannot have a charge which is 15.5 coulombs, right? Because you can't have a half E charge. Now that's a property of charge which is called being quantized. It means it comes in some fixed packet. You cannot cut that packet. Okay. Then we move ahead when we absorb these kind of ideas in the beginning, and these things are not very difficult to absorb. Then we come to the idea of electric force. Okay. Now, what is a force? A force is basically a disturbance which changes the state of motion of something. So charges, when a positive and a positive charge, when I keep them next to each other, they seem to go apart, they seem to push each other, they seem to repel. It means that they are applying some force on each other, right? Now the next logical question to ask is, how much is this force? Okay, so that has been quantified, and that was quantified by this physicist which I already named, Coulomb. And Coulomb said that when you have 2 charges, right, and such charges that they are very tiny, like they're almost like points, like if you have 2 protons or 2 charges which are almost point like, and say one is charge Q1 and another charge Q2. By the way, in this chapter you would notice that we represent charge usually by the letter Q. C is the unit, Q is the letter. I can say Q is equal to 5C. Charge is equal to 5 coulomb, 10 coulomb, 15 coulomb, 100 coulomb. Okay. So Q1 is one charge, Q2 is another charge. And if I tell you that they are separated by a distance R, okay, then what would be the force between them? So the force between them will be equal to some constant which is K times Q1, Q2 divided by R square. Okay. So you take one charge, you take another charge, you multiply the value of the charges, right? If one was 5 coulomb, another was 10 coulomb, so it will be 5 into 10, and if the distance between them were 2, 5 into 10 divided by 2 square times k, right? What is this k? This k is a constant. This k is called you can call it Coulomb constant or electrostatic constant, but this k is usually, which is interesting, the value of this k is 9 into 10 to the power of 9, first thing in SI unit. Second thing is that this k is medium dependent. Okay, so if these two charges are kept in vacuum, they would exert, or they would seem to exert, a different force on each other. And when they are kept inside glass, or if they are kept in air, or if they are kept inside water, they would seem to exert a different force on each other. Okay, so this k, first of all, is a medium dependent thing, but in vacuum its value is 9 into 10 to the power of 9. And another weird thing about this k is that this k is equal to 1 by 4 pi epsilon naught. Okay, 4 and pi, you know what they are. Epsilon naught, epsilon is a new letter which you might be using, because I think before you might not have heard of this. Epsilon is just I think it's a Greek letter. Okay, and epsilon naught means epsilon with a 0. So epsilon naught is called the permittivity of vacuum. It is just a constant. Its value is 8.85 into 10 to the power of minus 12 in SI units. Okay, so that's what it is. So what does the equation basically become? The force between two charges becomes equal to 1 by 4 pi epsilon naught, which is the value of k, q1 q2 by r square, right? That's what we have. But this is the force equation only in vacuum. When you go into some other medium, with this epsilon naught, you write an extra term which is epsilon r, which is called as the dielectric constant of that medium. Okay, so don't be confused with these too many things. So basically there are two charges. We are trying to find the force between these two charges, right? One q1 q2 distance is r, so k, or k is now written as 1 by 4 pi epsilon naught q1 q2 by r square. This is the force if these two guys are in vacuum. If they are in any other medium, you divide it by a value epsilon r, that is, it becomes 1 by 4 pi epsilon naught epsilon r q1 q2 by r square, right? Where epsilon r is obviously something which comes from the medium. It's called as the dielectric constant of that medium. For air, that is very close to 1. So most of the cases we don't differentiate whether things are in air or in vacuum, because the numbers are the values are very close. That's it. Then we talk about electric field. So what we did was, now electric force was an interaction between two things, right? So now we wanted things to be more refined. So what we did was, we said that we don't need two charges all the time to express what kind of effects a single charge can have. So if you have a 5 coulomb charge, let's say, imagine that a 5 coulomb charge is placed here. Now it's in its vicinity, anywhere in its vicinity, if I bring another charge, that is going to experience a force, right? Because of the Coulomb's law. Now, so there is basically a region around this charge. There's a region around this charge in which you can feel its force, right? The force which this 5 coulomb charge is in a way producing. So that region around the charge is basically a field, and that's what we call as electric field. Not technically, but that's the field, that's the region. But what happens is, now if 5 coulomb is fixed here, and from 5 coulomb I take a point here, a point in space, and if I keep there 10 coulomb, I know that it is going to experience a force 1 by 4 pi epsilon naught 5 by whatever the distance is squared into the 10. If it were 11 into 11, it were 12 into 12. So what I am seeing is, there is this factor which I always multiply with the charge which I am placing there. So I said, what charge I am placing there is irrelevant. This factor is this relevant, and this what factor is what? This factor is nothing but the force felt by a 1 coulomb charge there. So what you do is, you keep a charge and you define a region around it, and in that region, at any point in space, right, you say that I can define a quantity which is linked with every point in space. Okay, it's a quantity you're linking with every point in space, and that quantity is, it is the force experienced by a 1 coulomb charge which is placed in that space, in that point. Okay, and what benefit do you get? So you get that factor out. Okay, so whatever force a 1 coulomb charge will experience, you get that number. Okay, you call, actually that number is called electric field, right? Technically, that's what I said, that is not technical. And then if I say, oh, there I place a charge of 15 coulomb, then you just take that number and multiply it with 15, that you get the force. So electric field is basically the force experienced by a unit charge. Okay, so you learn in this chapter the electric field because of a single charge. Then you go into sphere, and there's a charge distribution inside a sphere. You learn things like inside the sphere the electric field is 0, outside the sphere behaves like a point charge, and then you solid sphere, hollow sphere, there are a lot of formulas. Then you learn things like if you have an extended, for example, you have like some kind of a line of charge. So charge is uniformly distributed on a line, and I want to find the electric field at this point. Then I cannot be like I cannot assume all the charge to be concentrated at a point. You can't do that. So what you have to do is you have to take a small element, and then you have to find the force, and you have to integrate. Okay, if you're preparing for JEE and all, integration might not be that required. Sometimes in boards they ask those kind of derivation, but you should know how to integrate. You should know the process of integrating. That itself is like choosing an element, choosing an axis. Then there's a whole flow for it. Now you learn all these things. You learn, you try to become comfortable with electric field. You try to become comfortable with an idea that electric field is not a property of anything. It is a property which we are associating with a point in space. Yes, it is created by charges which might not be at that point, right? Some charge is somewhere. It is creating a something which we are calling electric field at a point in space. So it is something which is associated with a point in space. Okay, that's an important thing which you need to know. Then we study that this electric field, which is everywhere in space, and every point in space can have this electric field, can be represented by electric field lines. Okay, so you draw these beautiful lines, you must have learned, which represents electric field lines, and if you take any point in any of this field line and you draw a tangent there, it gives you the electric field at that point. And then you see that the closer these field lines are, right, the greater is the electric field. That's how the field lines are designed in a way. And the far away they are, that's smaller the electric field is. So if they are like spread out, they are more spread out, and there's less crowded, it means electric field is less. And if they're very bunched up together and they're very close, electric field is more, right? And then you learn from this, if once you get comfortable with the idea of electric field lines, you kind of answer the questions like, why don't electric field lines cross each other? Because if they cross each other, at the point of the crossing, you can draw two tangents. That would mean two directions of electric field, but any point has only single direction of electric field. All those reasons you learn, and you basically become comfortable with the idea of electric fields, right? And then after that, you learn about electric flux. That is, if you take an area, how much of electric field is flowing out of it. That's the idea of flux. So if you take an area, and if there is some field lines passing through that area, so it's a rough measure of the number of field lines passing through that area, which is very rough, because how much number do you assign? That's also a subjective thing. It's not like a fixed number. So roughly it is that. And mathematically, which it makes more sense to talk about these things mathematically. Mathematically, if you have an area and you have electric field in that direction, electric flux is simply the electric field multiplied by that area, if it so happens that the area is perpendicular to the electric field. And if this area is not perpendicular to the electric field, if the area is like this and the electric field is like that, then you take the projection of the area perpendicular to the electric field, and you multiply the electric field to the perpendicular projection of that area to get the flux. And if it so happens that the electric field, because there are many cases possible, electric field might not be constant, the area might not be flat. So what you do is you forget about all this projecting and all that. You say that, okay, forget about all that. What I'm going to do, I'm going to pick a very, very small area, very small, and I'm going to say that in this very small area, electric field would more or less be constant, and here I will define my electric flux. So you define it as E dot ds, where ds is a vector. It is a vector which you define as a vector which is coming out of that area. It's the value of this vector is the value of the area or the surface area, and the direction of this vector is perpendicular to that area. Okay, so E dot ds is what you define. Then you study about Gauss law. Gauss law says that now till now we were talking about open surfaces. Gauss law says that I'm all about closed surfaces. Yeah, so now give me any closed surface, and you give me, and you find, and there is some electric field in the region, it's between some electric field lines, there's a closed region. It's an imaginary closed region. It might not exist. It's not like a polythene bag. It's a closed imaginary region. And he says that in that closed imaginary region, and if you find the flux over that closed imaginary region, over the surface of that closed imaginary region, then the flux of that closed imaginary region, that's called a Gaussian surface, will always be equal to whatever is the charge that region holds, or whatever is the charge enclosed by that region, divided by epsilon naught. You are already familiar with epsilon naught. So that's what it says. So basically what happens is, the way I interpret it, and because I cannot go into the details of a lot of things in this chapter, it's a chapter which is usually studied in, it takes around a month or so to properly prepare this chapter and solve all the problems. So what I'm telling you is some brief ideas about things you might have missed out in the classroom, or you might not have paid attention to. So when you have a closed imaginary surface, right, and you're saying that the electric flux over this surface is equal to the charge enclosed by epsilon naught, what you find is, if you have no charge enclosed, right, then the flux of a closed surface is going to be 0. Okay, why does that happen? That happens in a way, and this is just a qualitative idea, that happens in a way because you see that the electric field, if you imagination is very important. You imagine an imaginary surface here and an electric field line entering, right? That electric field line will pass through it and then will go out. So the contribution to flux which it gives while entering, it takes away while going out. And if it is a closed surface, it is going to go out of that surface somewhere. So everything that enters goes out. So there is no net flux, or there is, in a way you can say that from that closed region there is no net electric field flowing out or in. So it is like this. You take a wire mesh in the shape of a surface, like its shape of a closed surface, and you put it inside a river in which the water is flowing. Now if I ask you how much net water is flowing through this wire mesh, I would say, well, 0, because whatever water is flowing in is definitely flowing out, because there's no water which is getting generated inside it, or there's no water which is going sinking inside it, in the sense that if I had put a pipe inside that mesh, and that pipe had some water coming out, then I can say that there is some net water coming out of that mesh, because there is a source of water inside. There is a source of electric field inside. And what is the source of electric field? Electric charge. So if there is an electric charge inside, there will be some flux, and that's what Gauss law says. If there is no electric charge, it will be 0. Okay, that's one analogy to think about it. Okay, we learn about all these things, and then we learn about electric potential. So I want you to always have an idea. See, sometimes people get confused because there are so many things to remember. So every time you hear the word electric potential, I want you to think about work. Electric potential is always related to work. Okay, electric potential is basically the amount of, first thing you need to know about electric potential, it is defined between 2 points, A and B. There are 2 points. Okay, this is point A, this is point B, and the amount of work done in moving a unit positive charge from B to A, a unit positive charge from B to A. You have to do some work if there is a field, because it will apply force against force. If you are moving something, you have to do work. That's how work is defined. So you do some work in moving this charge from B to A, right? And whatever work you do is VAB, that is the potential of A with respect to B. It means that if you take something from B to A, this much work you have to do per unit charge. Okay, That's what potential is, nothing but work done. Okay. The fascinating thing about electric field is that electric field is a conservative field. It means that it doesn't matter whether from B to A I bring a charge this way or that way or this way, or whether from B I go travel the whole universe and then bring it to A, imagining that the universe only has a conservative field. Okay, it doesn't matter, the work done will always be the same. That's what conservative field is. The work done is independent of the path. Okay, so that's how you define the potential. And again, potential is like field, it is defined for a point. It's not a property of some object. Yes, it is created because of charges, but it is defined at a point. This point has this potential with respect to this point. Okay, usually what we do is we take this B at infinity, because we see that we are bringing it from very far away, and we assume that the potential at infinity is 0. So what we can write is VAB is equal to work done in bringing something from B to A divided by the charge, that is the work done per unit charge, and this is actually equal to VA minus VB. You can say that potential at A minus potential at B is equal to potential of A with respect to B. This is a way of writing it. Okay, and if you take the potential of B as 0, or potential of B if you choose it at infinity, you can just define an absolute potential at A. A lot of details are there about potential in that sense. Now you study potential for different kind of distributions. You study potential for a sheet, you study potential for a line of charge, and like that you go on. Then you study conductors, where you have some charge put on a conductor, and that you learn that the charge always comes to the surface, right? Because you cannot have an electric field inside a conductor, right? If you have an electric field inside a conductor, a constant electric field under electrostatic condition, then a current would start flowing inside it, and that would be against the law of conservation of energy. So from where that because current is energy, right, from where that energy is coming. And if you make a conductor really sharp enough, if you put too much charge on it, then the charge gets accumulated on the sharp portion, and it can ionize the air around it, and the charge can start leaking out. That phenomena is called coronal discharge. So this chapter is, I've just broadly touched upon this chapter. It has a lot of things. You start with charge, you have electric force, you have field, you have flux, you have field lines, you have Gauss law, you have electric potential, and then you have conductors, and in each set you must solve a lot of problems. And again, this is something I say again and again, that you might read a concept, you might really understand a concept, you might solve a couple of problems, but do not think that you have understood it unless you have gotten a real feel about it. Okay, in theory, if I teach you how to ride a cycle, and if you have ridden a cycle once, that doesn't mean that you're going to ride a good cycle. And when you are sitting for JEE, and let me be very blunt and clear, you are actually sitting for a competition. So you want to prepare for marathon by just knowing how in theory cycle works, and by just riding a cycle a couple of times, you're not going to win that marathon. You're not going to at least be in a good rank in that marathon. You have to practice again and again to get a good feel, to get that idea from the back of your head to come to the front of your head, so that it comes to your tips. Every time you see a question, it should just click to you. How should you approach that? And that doesn't come with genius. It doesn't come with intelligence. That comes only with practice. The more question you practice, what will happen is, once you see a question, you'd feel like, oh, I've seen this kind of question before. I know how to go about it. I'm not scared of it. Okay. So that's the story with electrostatics. I hope you had something positive to gain out of this session. Let me check if you have some questions. Yeah. So Siddhartha Basu has asked, are moving charges variable? No, Siddhartha, it is not a very well framed question, but I kind of get what you're trying to say. When a mass moves, sometimes we say that the mass changes, but you don't have to worry about that for a very, very long time, because this is a concern of special theory of relativity, which you don't encounter in 12th standard, but it is a good thing to wonder, and maybe if you can read in popular magazines, you can read about it. But charge in itself is an invariant quantity. It doesn't change. It doesn't vary. Okay, so charge doesn't vary. Jagdish is asking, if two identical conducting sphere let to contact each other. One sphere have 5 electrons, but after contact, what will be the charge distribution? Okay. So understand this. It's a good question, Jagdish. You are saying that if one has an extra of 5 electrons and the other has an extra of 0 electrons, and what we have learned is if they're identical, then what happens when you touch them? Equal charge distribution happens. If one had Q charge, another had Q charge, or another had 0 charge, when you touch them, Q by 2 is what comes. Now what you are putting me in a position where you are saying, what if it had 5 electrons? Then I think Jagdish, this will happen, that 2 electrons will remain here and 2 electrons will remain there, and 1 electron will remain exactly in between them. Okay, that I'm not sure if that happens, because this is not a microscopic phenomena, it's a macroscopic phenomena. Okay, it's a phenomena of not 10 rupees, it's a phenomena of 10 billion rupees. Okay, so majorly what happens is what we talk. Even when I say Q by 2 comes, in reality precisely Q by 2 might not come. In theory they come, in reality they may not, because there are different factors which we don't consider. We cannot consider it at this level, because we learn things by simple models first, and then we complicate our models, right? When you learn how to make an aeroplane, they first teach you how to make a simple aeroplane. How does a balloon fly? Then they simply complicate this thing. Now why you want to do this? So things get complicated as you move along. Models get more complicated as you learn more and more. You cannot be taught the most complicated model in the beginning, because you'll go bananas. Basit 1 is asking, in layman's language, what is a charge? In science, how can we define charge? Why 1 coulomb is not equal to minus 1.67 to the power of minus 19 charge of electron? What is Coulomb's law? That I have discussed. PS suggest a good reference for physics, class 10. I'm studying Pearson IIT Foundation. Okay. You're asking, Basit, in layman's language, what is a charge? Would a layman ever ask me, what is a mass? He might not ask me, right? I mean, mass is just there. You know, mass is just there. I mean, when the first time people have taught you that, you know, you have something of 10 kilograms, it is moving with this much acceleration, that this is F is equal to ma. Did you ask, what is mass? What is mass? Like, what is mass? Like, you explain me in layman's terms. You can't, because it's just a property of universe. I mean, why is it a property of universe? You can go to that level, but what happens? See, whenever in physics you're learning something, you always have a framework, right? So, for example, this will be very clear if I give you this example. Say you are teaching your younger brother a poem, okay, or some line or something, and he says, okay, so what does this word mean? And he says that this word means this. CAT means cat. Cat looks like this. Okay, and then he might say, okay, why is it CAT? You say, well, that's the way it is. And he might ask you, why C is written this way? Why isn't C written that way? You might say, you know, that's the way it is. That's the way it is. I mean, there's no answer to that. But again, C to be written this way is something we all as humans decided. But charge being there, mass being there, is something the universe has decided. And why is it there? It's a beautiful question, but it is outside the framework. We assume that it is there, from where we build our physics, and we talk a lot of things. But why is it there? That would require another level, and there we go in physics, but not at this level. Okay, so if you can pursue physics, it's a very wonderful question, though. It's not a bad question. Why 1 coulomb is not equal to this? This is also a good question. Why don't you define 1 coulomb to be the charge of electron, when you know that is the fundamental unit? The reason for that, Baswit, is I think it has a historical reason. Okay, you already had defined a coulomb before, and then you later you found out the charge of an electron, and then you saw that, oh, turns out that the actual thing is this many times the thing which we have already seemed to define, because we knew about charges before we knew about electrons. Right? We discovered electricity before we had discovered electrons. Electrons got discovered in the beginning of the 20th century, and electricity was known from in the 1800s as well. So that's one thing. Second thing is, I think it is also because a proton or an electron is really tiny, and the level at which we discuss questions would be like is where there are a lot of electrons. I mean, like even in a tip of a needle there are a lot of electrons, right? So if I had defined my unit there, then it would be like say this small sphere has 5 billion coulombs. If that was the charge of one electron, or 5 billion coulombs, that's very ugly to say, 5 billion, right? So that's why you don't do that. Okay, Sabir has asked a question. Sabir Khan, how to solve Kirchhoff's circuit, sir? This is also a good question. Keep exploring it. We'll do a session on electric currents, and then I'll answer this question, how to do Kirchhoff's circuit. So that's it. I hope you liked it. I hope some of your answers were answered, and if you're not, please go on searching. The search should never end. Please do check out our YouTube. There are a lot of interesting videos we keep sharing all the time, and we put a lot of effort. We do a lot of animation and a lot of shoots, and to make things as interesting. They are not usually as dry as you find them in books. And download our apps and check out all the videos that we have made for different chapters in physics, and subscribe to our YouTube channel, as I said, and keep following us on our Facebook Live on BYJU'S JEE. Thanks.